People on Zoom, can you hear us?
Bob, can you hear us?
Hi, Bob. Can you hear us?
I was going to.
Signing over the.
Yeah, half the time I choose sugars, the other half I choose hard, like a mile away. Yeah, I had to do that. The first thing is like, so like, I
Oh, yeah. I looked at it, I was like,
Maybe it is.
I got.
I was saying that this is bad rumors.
This is one thing.
I was going to, but did anyone else pick up a blue book? Find any stray blue book, just bring them to the front and I'll take care of it. That's okay. I hope you did your reading. I get on the one hand.
All right, so I think that 27 more people pick up their copy. So if everybody quiets down, I can introduce the speaker for today. All right, so we are very fortunate to have today Andrea Alù, Professor Alù from City University of New York. He is the founding director of the Polaritonic Initiative in the Advanced Science Research Center there, and also Einstein Professor of Physics at the CUNY Graduate Center. So Professor Alù, started his career, let's say, from he did his bachelor and PhD at the University of Rome, in Italy, and from there he came to University of Pennsylvania as a postdoc. a couple of years. And soon after, he became a new minted professor at University of Texas at Austin, where he was roughly for about 10 years, he was actually. And in about 5 years ago, in 2018, he moved to City University of New York and Manhattan near Columbia University. Most of you probably know that. And that's where he's working on this topic of metamaterials and a lot of other interesting problems. Some of them where our work actually overlap to some extent. I'm very pleased that he accepted my invitation to come here. And with that, I invite Professor Alù to
Thank you. Thanks, Professor Agarwal, for the invitation. It's great to be here. What do you do? There is a way to remove this. Anyways, it's great to be here. It's amazing to visit Rochester with a great tradition on optics over many years and connect. We are actually not that far away and tell you a bit of what we've been doing in the area of metamaterials and engineered structures to manipulate and control light. If someone knows how to remove that.
Yes, I think it can be removed from the top. I think that's so. I really work before it.
Okay.
And then there's a high.
It makes sense.
Relax them down.
Okay, yeah. Thank you. Perfect. So I don't need to motivate here why controlling light is important, right? A lot of industry around in this area in particular and across the US and the world is very interested in leveraging the enhanced control of light that the devices are offering us for purposes from energy, very important to engage with extracting energy from solar, from thermophotovoltaics, imaging, sensing, communications, particularly important. Today, you may have seen the new announcement of the Apple augmented reality tools, right? So we're really in a time in which photonic technologies are exploding and address many of our societal challenges. So the quest is, can we build better technologies to take full advantage of the power of light in its various forms? And what is remarkable is that many of our the materials that we use for these technologies are actually quite common and quite limited in their use. The dielectric materials that typically we use to govern visible light or near-infrared light have a range of indices of refraction that is very limited. These days, new materials are starting to pop up that offer interesting opportunities, but it's really the start of a new era for photonic technologies. The limited set of material properties that help us build our photonic technologies ends up with footprint needs. So to build a very good lens for a camera, you end up with structures that have to stick out, and typically you cannot afford to put a lens like this on a cell phone. Or vice versa, if you want to get a very sophisticated control over light flow, you need to build a whole optical table full of devices. So can we come up with new materials, engineered materials, that can actually offer new type of responses that can shrink the dimensions of these structures without sacrificing performance, or even achieve new forms of control of light over small scales? And that's the field of metamaterials. So this meta stands for beyond. If you're not familiar with this term now, it's a buzzword that has been around for over 2 decades. And the whole idea behind this terminology is that you can start from regular materials, but with sophisticated engineering of optical modes and carefully playing with the symmetries and the localized response of these structures, you can actually engineer new platforms that offer optical properties are not available in natural materials. So these are some examples. There are many groups all over the world. It's really a field that has flourished in the last 20 years or so. And traces back, by the way, to the field of composite materials and of engineered structures. Photonic crystals as well are now a subclass of these metamaterials. I want to give a few snapshot examples of what we've been doing in this area and what we're excited about in the context of metamaterials. And one of the fields that has been mostly inspiring the broad community, even the industry has a lot of interest in these topics, is the concept of metasurfaces. So metasurfaces are structured surfaces rather than materials. So rather than building a bulk medium, you can just build through nanoimprint or through e-beam lithography, lithographic techniques, surfaces that are designed to structure the wavefront of light point by point. In fact, with quite a drastic resolution, given advances in nanofabrication. And the general idea is that you can actually take an arbitrary beam coming in and pattern a wavefront that can be a focusing wavefront, an hologram, or a multiplexing beam. The common approach to do this, and there are fundamental limitations as to how much you can do within a very thin platform, is input and output controlled by the same pixel, by the same localized nanostructures. So the whole idea, and you see it in this type of structures, is to engineer at the nanoscale a nanostructure that can support enough strong over resonance such that when a local electric field hits this point, it will transform it into something else, just scattered from the surface. And this function tau of x controls at that point amplitude, phase, and polarization of the response. That's how most metasurfaces are designed today. What we've been excited about is to go beyond this paradigm of local design of metasurfaces and actually empower the fact that these structures inherently have coupling between elements, in fact, leverage that coupling, and realize what we call non-local metasurfaces. So metasurfaces in which we actually control the coupling between many points with this convolution, or more generally, this kernel that relates inputs in many points to output at an arbitrary location. This addresses one problem of local metasurfaces, chromatic aberrations. Typically, the fact that you are localizing fields at a subwavelength scale implies strong resonances that have a frequency dispersion that you cannot really control. So at one frequency, these devices work very well. When you detune the frequency, the response is distorted, typically in a way that is undesirable. And ways to correct this require actually to sacrifice footprint again. So you end up again with bulky structures. In non-local metasurfaces, we use a different approach. We actually start from very delocalized resonances that connect points that are very far away in the aperture. They are driven typically by periodicity, by long-range resonances, like a grating. And then we locally control that response by perturbing it through perturbations that do not affect the coupling, the long-range coupling. So we can engineer the long-range interaction, at the same time get sub-wavelength resolution control over the spatial response. So things that we can do is to build a surface that is transparent to frequencies that do not engage this delocalized mode, but at the frequencies of interest, pattern it arbitrarily in terms of amplitude, phase, and polarization. And I will show a couple of examples of this. One way of doing this is to start again from a grating. So we're probably all familiar in the field of optics on how a grating works. You start from a completely periodic structure that a certain frequency can support a very strong resonance, especially low contrast gratings are very good at getting sharp frequency responses. What's remarkable of a low contrast grating is that each unit cell of that grating does not actually scatter much. If you excite just one unit cell in free space, you don't get any response essentially. But it's this long range periodicity, large aperture that give you that strong resonance, can be very remarkable strong response. However, now we can introduce tailored perturbations in which the symmetry plays a very important role to preserve that long range coupling, but at the same time outcouple this strongly confined mode in a desired way, point by point, with a different structure. So the resulting surfaces are completely non-periodic. Each pixel can be independently controlled, but yet that perturbation does not change the long range coupling. And you can control with this technique phase, amplitude of the response, and polarization. This is a first example of a meta lens. Many of you may have heard the term meta lens. In the field of metasurface, it's a big deal. There is even a company, Meta Lens, from a spin-off of Federico Capasso's group at Harvard. The conventional way of building meta lenses is to pattern an aperture with the resonators that are tailored to provide a parabolic phase profile. That's the distribution of phase that gives you focusing. So that squeezes the typically bulky lenses into a very thin planarized surface. This one is also a meta lens, but it's built in a very different way. Now we start from a completely periodic structure that the only thing it does is that at some frequency, it will reflect a lot. At other frequencies, at most other frequencies and angles, transmits a lot. That's for one frequency and one angle of incidence has a very strong reflectivity. That we know how to do. But then we pattern the perturbations on the aperture to actually provide that phase control. And we do it through what is called the geometric phase. So we pattern these perturbations in a way that we can rotate them across an aperture. And then for circularly polarized light, that rotation corresponds to a phase delay or phase advance. With that, we can pattern the phase across the aperture and get a nice focus. It does not come from individual resonators in which the coupling between them is a nuisance. It's something we want to avoid. It detunes the response. It's actually a type of response that depends on the long range periodicity, but that is controlled through the perturbations across the aperture. And for this specific design, we cannot get more than about 10%. In a purely mirror symmetric structure, circular polarization cannot be engaged more than 25%. So that's why this one is not a very efficient way. We can address it. I will show you in a moment how to do that. But what is remarkable compared to a regular meta lens is that here, as soon as you detune the response, the surface stops reflecting. It's transparent. You may say, what do I do with that? It's a very narrow band response. Well, the good news is that I don't engage these other wavelengths. So I can now design other metasurfaces on the back that can do either the same focusing for another wavelength or can do another functionality. So this is actually, I mean, in this paper, we showed you can stack 3 of them and do 3 independent things on neighboring frequencies. This one is the same concept, but a different frequency regime. This is done for millimeter waves. So it's a 20 gigahertz radiation. Here, the trick that we use is to actually break also that mirror symmetry in the longitudinal direction. And that allowed us to get 100% efficiency. Now you breaking that symmetry, you can truly get 100% reflection from a periodic structure for circularly polarized light. And if we do that, then we know how to pattern the array with subwavelength perturbations. And this gives us, for instance, beam steering to the left for this. This is a measurement for this metasurface, beam steering to the right, and focusing. So 3 different metasurfaces that do different things to either the same frequency but different polarizations, or the same polarization but 2 different operations. The trick is that these delocalized resonances can be very selective to polarization and to frequency. and even to wavefront in general. This is actually a measurement of the spatial focusing in real space. This is another example of a non-local metasurface. Here we pattern an aperture that is fed from the side rather than from free space. So we call this a non-local leaky wave metasurface. The idea is that because these modes are so confined to the surface already, you can actually feed them from guided mode. So this become like a very advanced grading couplers. If you are familiar with a grading coupler, is a typically grading structure that takes a guided mode and beams it at a certain angle, at a certain frequency. Here, this acts like a grading coupler, but it can pattern arbitrarily the radiation. So in this case, to demonstrate the complexity of the patterning we can achieve, we feed the surface from the side, but we design it to produce 4 independent holograms that are encoded in 2 different polarizations and in 2 different planes. 2 are amplitude holograms, 2 are phase holograms. So you feed the beam from the side, and as it populates this leaky wave mode, it creates in far field and normal incidence 4 independent patterns. These symbols are chosen to indicate that we control per pixel the amplitude, the phase, and the polarization state. These 2 variables are the coordinates on the Poincaré sphere of the leaked radiation. This one is an analog design, but this works for, again, millimeter waves. I'm jumping from optics, this from 1.5 microns to 20 gigahertz. Each of them have its own complications and advantages. Of course, doing experiments at 20 gigahertz allows you to realize larger structures. The wavelengths are much, much longer, so you can actually carve this on a copper film. You don't need the nanofabrication. The disadvantage of such a structure is that you need to make the perturbations stronger to be able to efficiently outcouple the energy as you feed it from this point. This total length of this structure is only 16 wavelengths. So in 16 wavelengths, you need to be able to leak out. And in this case, to demonstrate again the 4 degrees of freedom that we control out of these perturbations, we show radiation of focusing of in 2 separate distinct points of choice, 2 different circular polarizations of light. Another advantage of this type of non-local patterning of resonant modes is that you can use them to tame incoherent sources of light. So all the results I showed you so far rely on the fact that the excitation is something external from the metasurface, typically driven by a laser. So it's a coherent light. You are assuming or inherently implying that the impinging wave is coherent across the aperture, and you are just controlling the amplitude and phase of scattered light. However, the most common form of light, sunlight, light coming from hot bodies, thermal light, or photoluminescence, is incoherent. That's, of course, a more ubiquitous and more cheaper form of light. The question is, can we extend these concepts to metasurfaces that are populated by this type of incoherent oscillations of matter that drive this form of radiation? And in fact, already 20 years ago, Jean-Jacques Greffet has shown that if you take special materials, in this case silicon carbide, and you carve a grating on top of it, the periodicity of the grating can be used to outcouple the strong vibrations of the lattice of silicon carbide that are connected to thermal vibrations to beaming. So he showed that this type of corrugations over a silicon carbide surface can realize very directional thermal emission. That is counterintuitive because this thermal emission is supposed to be incoherent. It's supposed to emit everywhere in space with all polarizations, unpolarized responses, as well as without temporal coherence. Now, can we use the concepts of non-local metasurfaces to engage this form of incoherent light. And actually, it turns out that the answer is yes. The modes that are discussed are modes that are trapped to a surface with very large quality factors, and therefore they don't need to be populated by coherent light. They can be actually engaged by thermal oscillations of matter or photoluminescence. So the idea and the experiments I will show you in a moment are driven by the fact that we take a conventional material. In fact, all the experiments I showed are based on silicon, not even sophisticated phonon materials or materials that support very strong coupling of light with these thermal vibrations, but rather simple silicon patterned over a film can be engaged to emit thermally narrow band, so high temporal coherence, directional or even arbitrary wavefront shape and arbitrary polarization of light. So you can transform this incoherent into radiation. In this paper, we showed theoretically few designs of, for instance, spin-selective unidirectional emission from a silicon metasurface at a certain angle with a certain polarization of choice. This is a thermal metal lens that can focus light at a certain height. As you hit the surface, passive surface, and it focuses thermal light. This is an orbital angular momentum emission, so something that actually spins, creates a vortex in space that carries a net spin momentum as it emerges from the surface. And these are actually some experiments that point in this direction. These are 6 different metasurfaces that are designed to target a specific polarization of emission. So this shows that you can arbitrarily select the polarization of emission and emit it efficiently close to black body levels, so from just a silicon pattern surface. So each of these 6 measurements indicate one state of polarization across the Poincaré sphere. And then what we realized is that we can actually introduce a geometric phase similar to the phase I showed you before to control scattering from an aperture, but for thermal light. So basically, if you work around the region for critical coupling, that is the condition, the parameter condition in parameter space that gives you black body thermal emission, emissivity equal to 1, with this tool of playing with the rotation of these perturbations, you can actually access different phases of that response. So this example, you see 6 or 8 different variations over the structure, the nanostructures that we pattern over the surface that all guarantee the same state of circular polarization of light emitted, but with a 2 pi phase shift. So you can really control the way in which the wavefront emerges from the aperture. These are experiments. In this case, we patterned the metasurface that has a linear gradient of phase. And the theory would predict a typical dispersion from the grading that has a minimum not at 0 degrees, but at an angle. So you will have, if you operate at this frequency, you would have a tilted directional beam with very high temporal coherence and also spatial coherence. These are simulations in which, of course, these are a little bit polluted by other small resonances, but there is a clear preference towards radiating in certain directions and with a certain spin, certain polarization. And these one are experiments that demonstrate above a quality factor larger than 100 and a clear polarization selectivity in the thermal emission. Having this tool, you can actually build arbitrary operations over these thermal metasurfaces. These are other experiments in which we did something a little bit more sophisticated. We extended the concept of Rashba effect to thermal emission. So the conventional Rashba effect is the idea that you can build a metasurface that when you shine light onto the aperture, coherent light, you would get one circular polarization going left and the other circular polarization going right. Applying that to thermal geometric phase concept, this is actually the result. You see that you heat up the surface and one beam comes up on one side with one handedness, the other component with similar efficiency is radiated in the opposite handedness symmetrically. So this is what we call the thermal Rashba effect. And then we were able to also extend this to arbitrary polarization states. So you can actually come up in general with elliptical polarization emitted at one angle and the orthogonal state in the other angle. So these other two metasurfaces show two examples for linear, horizontal, vertical, and for two oblique, for plus minus 45 degree orientation. Again, demonstrating large thermal emission close to black body with this asymmetry in the emission. Now, all these principles that I showed you for free space radiation, for guided modes, and for thermal emission, so for incoherent oscillations of matter, all rely on starting from a highly delocalized resonance, typically trapped on a surface, and patterning it, pinching it point by point with perturbation. And what's crucial in doing that is the role of symmetries. If you do not carefully play with the symmetry class of each perturbation and its rotations, you are going to affect the coupling that you want to preserve, and the rational design of the surfaces rapidly breaks down. So what I want to show you next is that we can leverage these symmetries in extreme ways. And then just silicon, most of the designs I showed you so far are based on silicon, to leverage what naturally comes in some materials as an extreme asymmetry in response built in the crystal itself. To do that, I want to start from a theoretical surface, homogenized. So for now, let's forget that there are structures on it. If the structure is fully symmetric, then if I have an optical emitter that couples to the surface, this emits symmetrically everywhere. It's very similar to throwing a stone in a pond and looking at ripples that come out of the point of contact. If I now break the symmetry a little bit, so I change, for instance, the structure such that waves going in one direction are faster than waves going the other direction, these ripples become elliptical. And a good way to measure this lack of symmetry is to take the Fourier transform of the emission. Typically, you get what is known as an isofrequency contour. So it's plotted in momentum space. It's still done for a single frequency, but these two axes here are momenta, so are the reciprocal coordinates of the spatial coordinates. And for an isotropic surface, this is a circle. For an asymmetric surface, it would be an ellipse of certain eccentricity that depends on how different the response of the surface that can be described with this tensor R for electric fields along X and along Y. So what becomes very interesting is to think of materials that have an extreme asymmetry. And the largest degree of asymmetry you can think of is that one of these is positive, the other one is negative. So that's what you get in this response. What you get is that the optical emitter starts emitting light that is direct. In fact, if you take the Fourier transform, you get an hyperbola. You may think, what's the big deal about this hyperbolic response? The most striking aspect of this is that the amount of interactions that an optical emitter has with the surface, with the matter, the response of the surface, can be calculated at a given frequency as the integral over all momenta. So this isofrequency contour is a very good tool to study how much my optical emitter is coupled, can emit into the surface. And if I find an isofrequency contour that is an open curve, like an hyperbola, it means that I can couple a lot more energy, in principle unbounded. So these hyperbolic metasurfaces have been seen as a very good tool to enhance the coupling of light with matter based on extreme asymmetries. As a byproduct, you also get this directionality. So you don't even have to, you can send a lot of energy in the surface, but also it will go in specific directions. So that's something interesting and potentially exciting. What I want to stress is that this response is not single frequency. Across all frequencies for which this condition is satisfied, you expect to see this strong enhancement of coupling of light and matter and strong directionality of the fields. And this was, by the way, initially demonstrated experimentally by Hong Kong Park, this paper 2015, in which they demonstrated in these plasmonic nanogroove array, responses, as you see, it's broadband and it channels light in specific directions across many frequencies. By the way, incidentally, this is a way to do this type of response, because if you think about it, this extreme asymmetry comes from a surface that must be capacitive. It's an imaginary part of conductivity. Capacitive, when it's positive, means that the structure is basically before a resonance and inductive for the other response. And this, you get it from these grooves, because for electric fields parallel to these long ridges, you feel the metallic response of silver, that is inductive. But for electric fields orthogonal to these grooves, you feel the capacitance of the grooves that adds and makes it highly asymmetric. So you need very asymmetric type of designs. Well, what is remarkable in the last few years is that the whole optics community has been realizing that there are many materials that offer this type of extreme asymmetry naturally. And in fact, in many of these materials, at specific range of frequencies, you find extremely strong coupling of light and matter in a way that the optical oscillations cannot be distinguished from the material oscillations that light drives. In this regime, the light and matter form quasi-particles known as polaritons. And these polaritons can be associated with different forms of material resonances, from electron-hole pairs to excitons, to phonons, even magnons. I will show you a few examples of how metasurfaces and metamaterials can offer you, first of all, a good way of using this type of interactions of light and matter, but also push the field of metasurfaces beyond the current limits. In particular, I will show you a few examples of phonon polaritons, because phonons, basically, these are lattice vibrations, typically resonant in the mid-infrared range of light. This is already a very interesting range of frequencies for sensing and imaging. But what is nice of phonons is that they naturally are very directional, because these are basically vibrations of a crystal. So inherently, you have an ordered structure in which you are So over the past few years, there has been a lot of interest in these phonon polaritons, these strong responses of materials to light that couple to lattice vibrations. The material that probably has been most explored in the last few years has been boron nitride. So in the cubic form, of course, it's completely symmetric. So there is not much you can do. However electric field you excite it, you get the same strong resonance. The phonon is very sharp, but it doesn't really break symmetry. However, in the hexagonal lattice, it has a preference for one direction of the electric field. It gives you a lower resonance than for the in-plane response. And this already gives you the recipe. So along all this range of frequencies, this is known as the Reststrahlen band of the material. You are bound to find naturally in boron nitride hyperbolic mode, hyperbolic waves, directional waves. In this case, they have to go into the bulk of the crystal, because in plane there is no asymmetry, but out of plane there is. But then new materials have emerged that support also very sharp resonances. Look at, by the numbers of range of permittivity values that these materials can achieve. So very large quality factors. But the symmetries can be lowered more by the structure of the crystal. For instance, and these are, by the way, common materials. We use them every day in the lab, but not necessarily in this range of frequencies. This is silicon dioxide. This one, different from boron nitride, supports also a uniaxial response, so asymmetric in one axis, but this one is in plane. So interestingly, silicon dioxide already offers you the opportunity to get in plane hyperbolic responses without even needing for those grooves. This comes naturally in this Reststrahlen band. This one is calcite, also a very common material. We use it routinely for birefringence, but typically at optical frequencies, larger frequencies. Calcite ends up supporting this asymmetry. The beauty of calcite is that the axis of the uniaxial response can be tilted with respect to the interface. And this leads to other sophisticated forms of polaritons we have recently observed, called ghost polaritons, that come from this tilt angle, so this lower symmetry of the lattice compared to the interface. Molybdenum trioxide, I will show you in a moment some examples. These are three different resonances. So the three different axes have three different, so there are various Reststrahlen bands where you can find these responses. And more recently, gallium oxide in the beta phase offers a monoclinic response. In this case, actually, the lattice resonances are not even orthogonal to each other. So there is not really a specific plane in which you can find hyperbolic responses. You can get more intricate phenomena. And what I want to stress is that these are not even leveraging structuring. This comes from the lower symmetry in the crystal itself and the resonances that come for free with these phonon responses. So this is an example. It's similar to the structure I showed you before, but it's leveraging hexagonal boron nitride, and it does support this with the grooves, the hyperbolic response. These are measurements with a mid-infrared near-field scanning optical microscope demonstrating this beaming of light and this canalization, this very directional response of phonon polaritons that travel along this metasurface. Molybdenum trioxide, I was telling you, naturally, you don't even have to pattern. There is no groove necessary. Just the asymmetry of the two resonances in plane give you naturally this type of long range. So they survive actually several oscillations responses in plane, the hyperbolic naturally. And in fact, one way to exploit this that we proposed a couple of years ago has been to start playing with these geometries. So I was telling you what we're having fun with is special materials and symmetries, broken symmetries, and tailoring these symmetries together. So one thing we have proposed and also realized with molybdenum trioxide has been to take two of such surfaces. So first we had proposed it for our nano groove surface, and later we demonstrated it actually with molybdenum trioxide. Two of these hyperbolic surfaces, you stack them on top of each other and you twist. So this twist angle is a rational way to lower the symmetry even more. What can you expect from this twist and coupling of these responses? So look at how this is the evolution of the hybrid mode that comes from coupling these two hyperbolas. When the twist angle is 90 degrees, so these grooves or the principal axis of this hyperbolic metasurface are orthogonal, you get the two hyperbolas of the individual cell that you see in gray here cross 4 times. And when they cross, if the modes couple strongly, the modes repel each other. So you are engineering the hybrid mode, the result of the coupling through this repulsion, this engineered coupling. And actually the result is a mode that is very different from the hyperbolic initial mode. In fact, it's almost circular. You lose all the asymmetry. But as you change the rotation angle, this evolution of the mode drastically changes. You can actually control. You can go from a circular to an elliptical to a flat band to hyperbola, just by twisting the two surfaces. what's remarkable of this result is that this happens at the same frequency and with the same chemical composition of the structures, right? There is no change in the materials. It's really showing how this extreme modification of the response as a function of geometry. And this is not a single frequency response, it actually extends over a large bandwidth. So let me show you the experiments. This can be done in natural materials like molybdenum hydroxide. More recently, there have been a lot of papers actually demonstrating it also in other platforms using this concept of twistronics, so playing with this twist angle to modify the modal structure of the material. So this is the response of the single layer. You get this hyperbolic beaming on the surface that again you can measure with a scanning near field optical microscope. And these are bilayers in a hyperbolic, and then you go to flat band and to elliptical. So all these measurements are taken from the same materials, same thin films of molybdenum hydroxide, same frequency, but just different orientation of the principal axis of these lattice resonances of the crystal compared to each other in the film. When you go from uniaxial responses like molybdenum hydroxide, calcite, silicon dioxide to gallium oxide in the beta phase that is monoclinic, you add another degree of lowering of the symmetry. In this case, the lowering comes from the fact that the resonances, the detuned resonances that support this asymmetric response that gives you these hyperbolas are not orthogonal. And what's interesting is that you can still diagonalize the Hermitian part of the system, basically of the permittivity, so the reactive component of the response at each frequency. And provided that the diagonal component of the permittivity, so the diagonalized version of the permittivity shares opposite sign, you still get hyperbolic responses. But these hyperbolas have to rotate with frequency, because at each frequency, the diagonalization brings you to a different reference system. So the first interesting difference between a uniaxial medium and a monoclinic medium like gallium oxide, this twist in the resonances, is that the hyperbolas actually rotate. There is axial dispersion. As a function of frequency, these modes twist on the plane, remaining confined, remaining very directional. The second interesting aspect is that this coupling between resonators leads to a loss redistribution. There is one branch of these hyperbolas that suffers more loss, and the other branch that suffers less loss. The electric field here is less parallel to the two resonators that are more, that offer you some range of angles for which there is actually not much coupling with the losses of the resonance. This implies that you can actually push the emission of light in the surface further away. There is less loss and even more directionality, because you kill one of the branches. You put most of the loss into one of the two branches. So this is something we have observed. This is, for instance, a near field measurements. This is done in Berlin in Alex Parman's group with beta phase gallium oxide, demonstrating both this axial dispersion and this beaming of mid-infrared light at specific directions. And one thing we've been exploring is, can we now take advantage of this in metasurfaces? Can we tailor it with the strength we like to maximize this effect? So in metasurfaces, a good way of building an hyperbolic response is just take two resonators that are detuned and are orthogonal. Automatically you get hyperbolas whose dispersion remains fixed with the axis of the resonators, but changes the open angle of these hyperbolas. If you now add the rotation angle creates this twist. So now the hyperbolas can be very strongly confined. One of the branches can go much further than the other, and they can twist with the frequency. So it's axial dispersion and loss redistribution. And this is something we have observed. Here I show you first the simulations of what we expect for a small optical emitter All these simulations show the same resonators, so it's the same composition. Typical hyperbolic response to 50, 20, even 5 degrees. As you see, you get more slanting, more asymmetry in loss, and more confinement. Actually, you get more propagation, more quality factors as you change, preserving the quality factor of the resonator. In all of these, the loss in the resonator is the same. And in fact, if you integrate those over all momenta, you get a broadband enhancement of parcel factor. That's the coupling of the localized emitter with the surface. You get an increase in emission into the surface that is governed just by the angle. So the same exact structure, composition of the surface is just playing with the angle, pushes more energy into the surface because of the loss redistribution and the directionality of the response. To show you an experiment, the thing we've done already is to actually work with vibrations. So I was telling you all these mid-infrared theory and experiments with phonon vibrations. Now we'll show you macroscopic vibrations in elastic plates. So we go down in frequency a lot. We go to kilohertz frequencies, but we are measuring this using lasers. So we use what is known as a 3D laser Doppler vibrometer. So we send 3 lasers into a surface and we measure the mechanical vibrations of the plate as elastic waves propagate along the plate. So if you take surfaces that have orthogonal resonators, you will get again hyperbolic responses. This on its own is something actually remarkable. No one has observed before. And this, by the way, are measurements. You get these nice hyperbolic branches. But if you now look at you change the angle between the resonators, and this is a mass spring model, you will get asymmetry in loss, and you get more energy into one branch than the other. In the experiment, we realized this with, this is the plate where we measure mechanical vibrations. We load it with these teeth. These teeth are like resonators, are basically asymmetric resonators that depend on the polarization of the vibration. So they create this Reststrahlen band for these metasurfaces. And then we can twist one with respect to the other to control the angle between the two resonances. And by changing the angle, we can optimize the responses such that we observe both the axial dispersion and the increased directionality, the loss redistribution. So this is how the setup looks like. This is the source. Our optical emitter now is replaced by a broadband shaker that runs these vibrations. And this is the 3 heads of the laser vibrometer. These are the measurements as a function of frequency and angle. And what you see here is that for this legend shows that the different angles between the resonators, so the two surfaces that are twisted. You see that for 30 degrees, you get the largest axial dispersion. So as a function of frequency, you see that the hyperbolas twist the larger dispersion. The second plot summarizes the asymmetry in loss, the loss redistribution. And there is an optimal angle around 15 degrees for which the loss is all piled up into one branch and the other one is free to go. This is the maximum possible loss redistribution you can get. Is actually capped at 1. And you can prove for a passive surface, this is the best you can do in terms of loss redistribution. And the type of applications you can get out of this, if you come in from an hyperbolic medium into an isotropic medium, you naturally get negative refraction because of the different curvature of the two modes. With this, we observe it here. This is negative refraction. But with this twisting, we get a reflection-less negative refraction. Now, the beam that would be reflected here and here cannot be reflected because it belongs to the wrong branch. So you have a more efficient type of negative refraction. This is another application for non-destructive testing in which we exploit both the directionality and the axial dispersion. So these are actually measurements of the same sample in which we are changing frequency. And you notice that the beaming is tilting, so you can use this like a radar, as any frequency goes in a specific direction, and you can observe which ones will detect a localized defect on the surface that doesn't allow propagation of the wave transmission. Other couple of examples of polaritonic surfaces that now go a little bit higher in frequencies. One phenomenon that has been exciting the broad polariton community is the exciton polaritons. So now we're talking about typically 2D materials, transitional metallic cogenite in this case, that can couple light to material exciton resonances that can have also their own handedness. So one of the interesting prospects of this type of platform is that you can engage these resonances with handed light. So opposite handedness of light can selectively populate different excitons. And one of the visions for this field is that the valley degree of freedom between the two excitons can be used as a way to transfer information with a low energy form of information transport. A few years ago, with Elaine Lee in UT Austin, we showed that coupling this to an hyperbolic metasurface, again, one of these nano groove structures operating at the same frequencies in the visible, allowed us to actually enhance exciton photon coupling, but also to route it. So different handedness would lead to different directionality of emission and coupling to the photon response. But more recently, we've been working on the idea of coupling these 2D materials to plasmonic nanoscale resonances that can strongly enhance the fields at the nanoscale. So these are nanocubes that can provide selective polarization of the electric field. The enhancement here is in these very nanoscale gaps in the range of 10 nanometers, and can strongly couple light to these to exciton resonances in the WSC2, the monolayer underneath that supports these responses. What we were surprised to observe is that the coupling to the nanotubes brings an interesting family of dark excitons. Exciton resonances you will not be able to observe unless they are sitting into these very highly localized modes that come from the coupling of the nanocube to the metallic substrate. We observed thousands of times enhancement in emission. In fact, this part of this is the photoluminescent spectrum, and this central part has been divided by 450 times, otherwise it would dominate the response. So typically, we are used to look at these bright modes. These are out of the band of interest, and you see the emission is much smaller than what we expect, what we measure in this central region where the nanocube resonance is positioned. We have confirmed that this comes from the nanocubes. In fact, if you just look at the bright peak, you see that the nanocubes are dark. But when you look at this selectively in this spectrum, you see much larger emission that comes from the nanocube selectivity. It also demonstrates on-site selectivity of enhancement that comes from where the nanocube is positioned. We've done magnetic field measurements. So by adding a magnetic bias, you can actually study the nature of these dark excitons. They do not naturally emit because of their, they have a spin forbidden nature, but with the magnetic field, you can actually observe the emergence of the second branch, and from that you can actually measure the G factor of the dark excitons. And we have also shown electric control. So by gating it, you can actually dope these excitons and demonstrate different features. These are two different. One is a the first dark exciton, this is a trion, and they have different response with respect to the bias. In this first case, you have you switch it off as you dope it electrically. In the second case, you have this bistable regime as a function of the polarity of the applied voltage. The last example of a polariton that we've been very excited to study is the coupling of light to this other form of thin films, this 2D magnetic semiconductor, CRSBR. So these have actually a magnetic order, and there's been a lot of excitement lately in the condensed matter community in exploiting this type of van der Waals materials that have also a magnetic response. And you see here that as a function of the magnetic bias, the response of the material can be tuned drastically. Actually, you can switch from antiferromagnetic to ferromagnetic regimes. So very strong tunability and also very large anisotropy. So again, role of symmetries here is very important. Can we use light to engage this type of responses? And that's a work we've done in collaboration with Vinod Menon at City College, in which we looked at bulk CRSBR films, and we have studied the coupling to resonances, to optical resonances, basically Fabry-Perot resonances, either coming simply from the mismatch of the material, the index of the material with free space, or even adding actually metallic mirrors to enhance the quality factor. What we find is that the resonance of the material itself can be split into many resonances that come from the modes of these optical modes. And basically the exciton resonances sitting here can actually populate different fractions, the different optical modes. In fact, these are 3 different samples. This is just when the film is very thin, bilayer, you just get the exciton resonance. As you make it bulk, you get a lot more resonances that come from the optical response. If you add the mirrors, you make them even more photonic, more stronger quality factors. In fact, you can study now the response to the magnetic field. You can study how the change in magnetic order influences this response of the polariton, the coupling of the exciton to light. For instance, the exciton has the largest change of frequency with respect to the magnetic bias, but even all the other polaritons, even further away down here, maintain a dependence on the magnetic bias, and actually you can plot them. They follow this line. As you go away from the exciton resonance, the photon response becomes larger and more pronounced, but yet you get still an interesting effect that comes from the change in magnetic order or the tuning of the magnetic order. We have also studied the effect of time on this. So here we have modulated in time the magnetic bias and demonstrated both the coherent control of these responses, these fringes, some nanosecond fringes that come from modulating the system in time, and even demonstrating how the evolution of these response changes through incoherent changes that come simply from thermal responses, especially as the frequency grows. And this we found very different trends depending on whether we are in the more excitonic regime, closer to the exciton resonance, or further away in more photonic type of regime. So there is an interesting interplay that comes from leveraging these more sophisticated materials with photonic resonant modes. I think probably I'm up with time. Thanks very much, and I hope I showed you a few examples in which playing with symmetries and with the structured materials, photonic engineering can help you build interesting technologies for manipulating light at the X-ray. Thank you.
Thank you. Well, thank you very much for this very broad overview of the metamaterial. So, I mean, one question I wanted to ask you was the 2D materials, are they considered metamaterials nowadays?
I think they're an interesting platform, especially when you couple them to, I mean, these are basically starting points, right? Here we are just using simple resonators, but you can imagine that the next steps are to carve here nanoscale resonances and actually play with geometries. Right now, the geometry in this specific example is very trivial in a way. It's just a
the concept of metamaterials has sort of expanded. I mean, originally,
absolutely.
mostly just took a negative, refractive index. Now I think we can use it in a very different way.
Yeah, I mentioned it's a buzzword now, right? Anything that has to do with photonic engineering and coupled to. I think what I like of this is the idea that playing with symmetries, you can actually control light with great flexibility.
All right, let me open for questions. Yeah, I see a couple of them. Go ahead.
Hi, thank you very much. Face of the wavefront spatially. It seems that from my understanding, these non-local modes are tuned for a specific polarization. Does that mean that there's a fundamental limit if you have a non-polarized source to excite how much of the light you can actually couple and excite in that form, just based on what polarization is willing to accept?
Absolutely, that's a great question. Yes, so the control over phase and amplitude, it stems into specific polarization. So when you excite with unpolarized light, you certainly will engage only the polarization that matches with the mode that we have. The good news is that the other polarization does not even see the mode. So if you really wanted to build now a surface that the same thing for unpolarized light, you could just build two of these surfaces that engage orthogonal components and stack them, because the other one will just go through, will not even couple, don't see the response. So that's one advantage of this non-local approach to metasurfaces, that they engage selectively with light. So you are right, I cannot build over a single surface. I wouldn't know. I mean, maybe with interleaving, you could try to engage both, but certainly the solution I would offer is to just build two and stack. Actually, what's surprising is that they don't see each other. You can literally just stack them and they would engage separately the two components.
Further question, yeah, go ahead.
So you mentioned like one application is like you rotate two surfaces, like the geometry uses like fluid controls and directionality as an example. But this is reminding me of like graphene.
Absolutely.
Like how people like rotate and like. So I guess like have you tried to use graphene like in application or like?
Yeah, I mean we were clearly inspired by twisted graphene bilayers. Actually, the physics is very, very different. The idea is very inspiring of this twisted approach, because also in that case, the idea originally of Alan McDonald and then demonstrated by Pablo Herrero is that a graphene monolayer is supports a Dirac point, but so in energy, but the electron conductivity of the response. But when you stack two of them and you twist, there is the moire pattern that is formed actually by the crystal of graphene for a specific angle matches basically the length scales necessary to mold the dispersion of this electron conductivity. So you can create a flat band. What we observe here is very different. Actually, there is no moire pattern coming from the crystals that can actually engage light, because the light scales are much longer typically. The crystal lattice of bolenium hydroxide is too small to see anything at any angle, practical angle. But what we find is that this extreme asymmetry that comes from hyperbolas can be also used to realize flat bands. I showed you that there is a specific angle for which we go from this more circular geometry to a hyperbolic. That transition is also a flat band. So there are some connections in the math, like the topology of the response requires you to go through a flat band in a similar way as in graphene. But of course, graphene experiments refer to electrons, electronic responses. This one is actually photonic. And one knob that they don't have in the graphene experiments is that we have is the frequency. So what we show here is that as you change the frequency, that magic angle, using the terminology of twisted graphene bilayers, changes. It's not a fixed angle like in graphene, but every frequency across the entire Strahlen band of your material will have a different magic angle at which you find a flat band for light, not for electrons. So we don't have any superconductivity. The analog of superconductivity for us is this diffractionless propagation on the surface.
Yeah.
Okay, so first of all, it's very impressive, a lot of work.
Thank you.
Congratulations for your work. And I have a question regarding metasurface based on geometric waves.
Mhm.
So, first question, from what material it was made?
Silicon
Silicon.
nanostructure.
Okay. And the second comparison, where is the direction of liquid crystal geometric phase metasurface based on polymer liquid crystal with 100% efficiency, and lenses and comparison of.
Absolutely. So we were talking about this cholesteric, in which there is twisting.
Cholesteric pneumatic with photoalignment, made
Yes.
photoalignment. It's beam engineering company.
Yeah, no. In fact, there are connections in the way in which you also play with geometry there, right? The alignment of these highly polarized structures. I think the main difference is that these structures rely on resonances. Typically, the liquid crystals, to get strong responses, you either need large thickness. Like,
No, this is micrometer size thickness.
is it like Bragg reflection, right? It's more.
This is not break with the geometric phase.
Yeah, I'm happy to discuss more, but what I want to stress is that these structures are basically less than 100 nanometers in thickness. It's very compact, but certainly, in fact, by the way, there is maybe one thing that you may enjoy is when we were working, I only showed one picture at the beginning of this, this structure. This structure is a stack of resonant dipoles that are twisted. We use again this twisting. This was, we did this work 10 years ago or more. This has a lot of similarities with pneumatic liquid crystals in which you can select polarization. In fact, also for this example, you have a circular polarization selectivity over broad bandwidth. The difference between the two is that the level of bandwidth and selectivity that we get per wavelength of thickness is a lot larger here than it would be in a liquid crystal. Even if the math, when you write the math, it's actually similar. But the advantage here is that in a liquid crystal, each molecule doesn't have a lot of response, right? These structures are actually strong nanoscale resonators that engage more with light than would be a molecule in a liquid crystal.
If you have impurity, maybe, because in liquid crystal, 100% reflectivity.
No, yeah, I agree.
If compare the lens with the
And the advantage there is it's also tunable. That we cannot.
Advantage can be you can make building block with this material. How many nanometers? We
Absolutely.
have 0.9 micrometer, but it does not matter. Maybe it doesn't matter.
But the big advantage would be also to combine. Liquid crystals can be a great tunability knob to add here. Most of this stuff is actually static. So that's another direction that actually community is exploring, combining the two. But this is, certainly it's a great question.
Anything else? Let me see if there are any questions online here. Anybody from Zoom wants to ask? I don't see anything in the chat here. Hearing none, then let me thank again for
Thank you very much.
I was hard to figure this out. They're actually. And so I was like, I remember the first one. I remember I looked.
Yeah.
And I couldn't find like a better. I'm doing this wrong. But no, they used to be. Zero. It's a serious. Yeah, no, they're around at 20. I guess. Oh, I just wanted to double check. I was like, no, what this are like, I don't know. Yeah, those are way for world. I think it's the same company. Yeah. I just wanted to double check. Yeah.
You were only correct.
Maybe that was, I took some notes and stuff, yeah. I think,
Sorry.